Okay, we're going to look at a couple of Newton's third law scenarios. This is where we're going to have, instead of just one object, we're going to have a system of objects, and they're going to be connected together somehow. And we're going to use Newton's third law to help us with these. So remember, that's where if you have an object exerting a force on an object, then the other object is going to exert a force back. It's going to be equal magnitude, opposite direction. So we can use that to help us with problems. Okay. So in the case of this scenario, we've got two blocks. One has got a mass of 5 kilograms and one has got a mass of 1 kilogram. And they're being pushed across the table with an applied force of 25 newtons. Okay. So they're being pushed on a table. They've both got force of gravity and normal, but those are offsetting each other, so we really don't have to worry about those. So our forces acting are applied force of the push, and that's a push on both blocks. Okay. And then each block has got a force on the other block because they're pushing against each other while they're both being pushed. But the force of block 2 on 1 is going to be the same as the force of block 1 on 2. Equal magnitude, opposite direction. Okay. So when we think about calculating F net, it's mass times acceleration, but it's also our vector sum, which is going to be our applied force minus the force of block 2 on 1 plus the force of block 1 on 2. But these two are going to be equal to each other. So they're going to end up basically canceling out. And we're left with our F net of both blocks of our whole system here just being this applied force. So I can use that and the mass of my blocks to help me get acceleration. When you have a scenario like this and you've got a system, you got to add the masses up. Okay. So we've got mass of 5 and a mass of 1. So we're going to have F net of 25 newtons. Again, that's our applied force. Divided by my total mass is 6 because I've got 5 kilograms plus 1 kilogram. And when I divide that, I get 4.2. Okay, so that's my acceleration on the system, and both blocks are accelerating at that rate. Okay, so then if I want the force of each block on the other, I can get those separately. They should be equal to each other, so it'll be good to see if that's true. So I've got, let's say we're going to do block 2 first. That's our 1 kilogram block. Okay, so we just want the F net on 2. 2 is going to have an applied force in one direction. Okay, and then it's going to have a force of itself back on this block in the other direction. Okay. And that, I can set that equal to mass times acceleration for this block. Okay, this block is 1 kilogram. So I'm going to have 1 times my acceleration of 4.2. Remember I said that's the same for both blocks. Okay. And I'm just going to shift some things around here. I'm going to end up with the force of 2 on 1 equals, it's really going to be 25 minus 4.2. So about 21 newtons of block 2 on 1. Okay. And then 1 on 2 I know should be the same, but I'm going to go ahead and try and calculate that just so I can double check myself. So for block 1, which is my 5 kilogram block, okay, that one's just got the force of this block pushing back on it, so it's F net. So that's F net of block 1 is going to be equal to force of 1 on 2. which is also equal to mass times acceleration. Okay, so that gives me 5 times 4.2, because this one's got a mass of 5, same acceleration that we already figured out. And 5 times 4.2 is 21 newtons. Oh, thank goodness. Okay, so these two have equal magnitude, opposite direction force on each other. And then in the total system, those two cancel out. We end up with our F net on both blocks just being that applied force. Okay. Okay, another example really quick. We've got two blocks that are being pulled. Okay, so they're connected by a rope. And it's a light rope, which means it doesn't contribute any mass or anything like that to this situation. Okay, so one of those is 5 kilograms, one of those is 3 kilograms. They're being pulled by a tension of 15 newtons, and we want to know their acceleration. Okay, so same type of free body diagram. We've got tension, we've got the force of the 3 kilogram on the 5. We've got the force of the 5 kilogram on the 3. We've still got the same normal and gravity. I'm not going to draw those right now just because I'm kind of running out of space on here. Okay. So here I'm just asking what's our acceleration. Okay, so remember our F net of our whole system. That equals mass times acceleration for both blocks. And then that's the same as my force of tension minus force of 3 on 5. I'm just using their masses. Plus the force of 5 on 3. And those two are going to cancel each other out. So I'm just going to end up with my tension being my F net. So my F net equals 15 newtons. That equals my mass. Remember my mass, I got to add those two up. So that's 5 plus 3 times my acceleration. So my acceleration is going to end up being 15 divided by 8, 5 plus 3. And I'm going to get 15 divided by 8 here is about 1.9 meters per second. And I could go on and calculate these two individual forces of this one on this one and this one on this one. I didn't ask for that, so we won't do it, but we could do it similar to this problem. Okay. Okay, last one on the homework, just really quick. This is kind of a throwback. We've been doing some like this. We've got a velocity versus time graph of a box that's being pushed across the table. The box has a mass of 50 kilograms. What's the value of the applied force on the box, or F net? Remember, F net equals mass times acceleration. And I know what my acceleration is because I can get that from the slope of this graph. I can get that from my rise over run. So let's pick a point. This is a nice graph. We've got multiple points we could use, but we can just use this one to start with. So my rise here is 4 meters per second. Okay, and my run is 2 seconds. So 4 meters per second divided by 2 seconds is going to give me 2 meters per second. That's my acceleration. So I can multiply 50 by 2, and I'm going to get 100 newtons as my applied force. Okay, so just remember, use that slope to your advantage. You can use it to help you solve that problem.